Welcome to video lecture on groundwater engineering. We will see the hydrological parameters. Introduction to groundwater engineering. Groundwater is a precious and most widely distributed resources of the earth, and unlike any other mineral resources, it gets its annual replenishment from the meteoric precipitation. The world's total water resources are estimated as 1.37 into 10 power 4 million hectare. Of these global water resources, about 97.2% is saltwater, occurs mainly in oceans, and only 2.8% is available as freshwater at any time on the planet Earth. Out of this 2.8%, about 2.2% is available as surface water and 0.6% as groundwater. Even out of this 2.2% of surface water, 2.15 is fresh water in glaciers and ice caps, and only of the 0.01% is available in lakes and reservoirs, and 0.001% in streams, and the remaining being in other forms. Out of 0.6% of stored groundwater, only about 0.3% can be economically extracted with the present-day drilling technology, and the remaining being unavailable as it is situated below a depth of 800 meters. The amount of groundwater within 800 meters from the ground surface is over 30 times the amount in all freshwater lakes and reservoirs, and about 3000 times the amount in stream channels at any one time. Diagrammatic representation of these global water resources. So the Venn diagram shown here shows the hydrosphere, in which 97.2% was occupied by the salt water in oceans. Only 2.8% is fresh water available globally, in which 2.15% is in the form of ice and glaciers. Only 0.62% of water is available as groundwater. At present, nearly 1/5 of all the water used in the world is obtained from groundwater resources. Agriculture is the greatest user of water, accounting for 80% of all consumption. It takes roughly 1000 tons of water to grow 1 ton of grain and 2000 tons to grow 1 ton of rice. The present irrigated area in India is 60 million hectares, of which about 40 is from groundwater. The average annual rainfall of India is around 114 cm. Based on this, it is estimated that the total annual rainfall over the entire country is of the order of 370 million hectare meter, and 1/3 of this is lost in evaporation. Of the remaining 247 million hectare meter of water, 167 million hectare meter goes as runoff, and the rest of 80 million hectare meter goes as subsoil water. Out of this 80 million hectare meter of subsoil water that seeps down annually into the soil, about 43 million hectare meter gets absorbed in top layer, thereby contributing to soil moisture, and the balance 37 million hectare meter is contributed to groundwater from rainfall. We will see the groundwater potential of India. So about 2/3 of the total land area in the country comprises consolidated formation, in which 75% of this being made up of crystalline rocks and consolidated sediments, the remaining 25% being the trap. The remaining 1/3 of the total land area comprises semi-consolidated and unconsolidated formations like alluvial tracts. There is ample scope for the development of groundwater in these areas. Groundwater potential of Tamil Nadu. Tamil Nadu constitutes 4% of India's land area and is inhabited by 6% of India's population, but has only 2.5% of India's water resources. More than 95% of surface water and 80% of groundwater have already been put into use. Major uses of water include human or animal consumption, irrigation, and industrial use. The utilizable groundwater recharge is 22,423 million cubic meter. The current level of utilization expressed as net groundwater draft of 13.558 million cubic meter is about 60% of available recharge, while 8,875 million cubic meter is the balance available for the use. Over the last 5 years, the percentage of safe blocks has declined from 35.6% to 25.2%, while the semi-critical blocks have gone up by a similar percentage. The over-exploitation has already occurred in more than a third of the block, and while 8 blocks have turned saline. We will see the water-bearing properties of rock. There are some clues or ideas regarding the water-bearing properties of rock. It is the perviousness and not the porosity which is significant in water yielding of rocks. The principal factors affecting porosity are grain size, shape, grading, and the amount and distribution of cementing materials. Fissures, joints, bedding planes, faults, shear zones, cleavages, vesicles and solution cavities, etc. all contributes to the perviousness of the rock. The image shown here is the soil particles or atmos with pores, fine pores into the body through which the water will flow. Then, besides weathering and texture, the presence of numerous sets of joints, fractures, cleavages and fault breccias form the good water-bearing zones in igneous and metamorphic rocks. Solution openings in limestone and dolomites may yield water. Limestones with cavities are formed due to the action of acid waters. In consolidated formations, water may be yielded through cracks called fissures or crevices. Basalts form a good source of water since they invariably contain vesicles and are easily susceptible for weathering. Water in the shale is found in the joints. Shales invariably develop two sets of joints. In such cases, open dug wells of large diameter are preferred. Selection of well sites in shaly region must be done carefully, recognizing the storage, infiltration and seepage. Sandstones form very good aquifers. The porosity of these materials depend mainly on shape and arrangement of the constituent particles, cementation and compaction, degree of assortment and fractures and joints. Poorly sorted and well cemented sandstones are poor aquifers. The most important water yielding formations are the unconsolidated gravels, sands, alluvium, lake sediments, glacial deposits, etc. Marble with fissures and cracks, weathered gneisses and schist, heavily shattered quartzites and slate serves as good aquifer. Faults generally affect the water table by blocking or diverting the flow, sometimes provide an outlet to underground water that would not otherwise be available. The most favorable of all sites for a well is provided by a synclinical trough of alternating layers of permeable and impermeable bed of rocks providing artesian condition. A series of dipping formations which include a pervious or water-bearing stratum which with impervious beds above and below, the outcrop of the pervious bed receiving supply of water from the surface form the artesian conditions. Most of the water in crystalline rocks is within 90 meter and in sedimentary formations, wells drilled deeper than 600 meter yield little water. The quality of water in the well depends on various types of rocks encountered. Sometimes a small band of impervious strata above the main groundwater table holds part of water percolating from above. Such small water bodies of local nature which cannot replenish quickly are called perched water table. Such water bodies are highly deceptive and misleading in groundwater exploration works. Swarming of insects in the evenings at certain points on the surface during the dry season and existence of green grass vegetation are the indications of a perched or suspended water table. Springs are formed when groundwater starts oozing out from the ground surface. Aquifer and various terminologies related to water-bearing strata. Aquifer, sufficient saturated permeable material to yield significant qualities of water and wells. It is derived from the Latin word aqua means water, fer means to bear. Say, for example, unconsolidated sands and gravels are aquifers. Aquifers are generally overlain or overlain by confining bed. Aquifers are broadly classified into confined and unconfined aquifer. Unconfined aquifer, it is permeable formation that contain Phreatic surface, that is the water table, has an upper boundary that fluctuates in response to recharge or discharge. Perched aquifer, a special type of unconfined aquifer which occurs when the precipitation moving downward intercepted by a layer of relatively low permeability. Example, a layer of clay within sand. Confined aquifer. The aquifer is completely saturated and does not have a free water table. The confining layer generally divided into a cichlid, a saturated but relatively impermeable material that does not yield appreciable quantities of water to wells. Example, clay. So the word is derived from the Latin word clod, derived means shut or close. Aquifuge, a relatively impermeable material neither containing nor transmitting water. Example, granite. Aquitard, a saturated but poorly permeable stratum which impedes groundwater movement and does not yield water freely to the wells that may transmit appreciable water to or from adjacent aquifers. Example, sandy clay. Aquifer properties. Permeability. It is the ability of the formation to transmit water through its pores when subjected to a difference of head. It can also be defined as the flow per unit cross-sectional area of the formation when subjected to a unit hydraulic head per unit length of the flow. So the factors affecting permeability. Permeability depends on the grain size distribution, porosity, shape and arrangement of pores, properties of pore fluid, temperature of fluid and entrapped air. Method of estimation. In the laboratory, the permeability of relatively coarse grained soils can be determined by a constant head permeameter by measuring the volume of water percolating through the soil sample of cross-sectional area A and length capital L in a given time t under a constant head h. So from Darcy's law we have QV equal to Q into T. So Q, the quantity of water collected or passing through the soil sample, is K into AH by L. So finally we can find the permeability as K equal to VL by HA into T. In relatively fine grained soil, it is not possible to collect an appreciable volume of water to be accurately measured. The permeability is determined by a falling head permeameter. If H1 and H2 are the initial and final readings respectively in the standpipe of cross-sectional area A in a time t, the above soil specimen of length L and cross-sectional area A, the permeability is given by K equal to 2.303 AL by AT log H1 by H2, where H1 is the initial head and H2 is the final head. The constant head and falling head permeability test is shown in the figure. So for conducting the test, the soil sample should be well saturated before the readings are to be taken. Permeability is also be determined in the field by pumping test. By supplementing a few field tests with laboratory permeability data on samples collected, representative of at least all major textural units within the area of study and geological interpretation, the permeability or transmissibility of the aquifer can be obtained. So the image shown here is a test well and an observation well. In the test well, the water will be pumped and then draw down, that is the lowering of a phreatic line, that is the water table, groundwater table, can be noted down from the test well, so in which the permeability of the given soil sample can be estimated. Even though the soil sample collected through the pumping test and it can be compared with the laboratory permeability data from which the type of soil and its porosity can be estimated. So thank you for watching this video.